During cold working, as the degree of slip increases with increasing cold work, the deformation of the grains becomes more severe. Eventually, the deformation of the grains is so severe that it causes the planes of atoms to lock up. Locking up of the planes resists further deformations. Locking up resists further deformations. So the force to slip the planes of atoms increases. As the severity of the deformation increases because of the lockup, this is the lockup of the planes of atoms, effectively the new flattened shape becomes more and more resistant to further deformation. The forces required to induce more slip, more shape change, increase with increase in deformation. So the more we deform a metal, the more the force required to deform the metal further increases. Thus, cold work and the resultant slip causes a strength increase. If we cold work a metal, we deform the grains. Any further work requires higher force to deform the grains. The higher force increases the strength. We term this cold work strengthening increase work hardening or strain hardening. So when we cold work grains, we work harden or strain harden them. Work and strain hardening are both have the same meaning. So when we cold work a grain, we deform it. We strain harden or work harden it. Because we strain harden or work harden it, the deformation for further deformation increases, so the metal becomes stronger. Any mechanical cold work deforms the grains. And cold work involves reshaping, reforming, and cutting at room temperature. Cold work hardens the metal. And in this picture, you can see a piece of aluminium that has been cut along the edge with scissors. And you can see the effect of cutting the aluminium on the work hardened edge. Cold working distorts the grains in the direction of the major deformation, that is rolling or drawing. So by cold working, because we're working the metal and it is moving in a direction, we are introducing directionality into the grains of that metal. When you roll, you reduce the slab thickness as the metal volume remains the same. The rolled sheets grow in length. This results in the grain stretching, slipping, elongating in the direction of work. This introduces strong directionality. Now, when we roll a slab, we control stop transverse movement. So when we roll a slab, we reduce the thickness. We roll the slab so it grows in length, but we constrain the sides so it doesn't move transversely. So we restrict the spread sideways, so growth is longitudinal. So the strength increase will be marginally greater longitudinally than transversely. That is because the transversal sidewards deformation is minimal, so the resultant cold rolled properties transversely to longitudinally will be slightly different. This means that cold worked metals exhibit directional properties in the direction of maximum cold work. We've mentioned that when we cold work, we deform the grains and increase the strength of the metal and deform it. So the greater the cold deformation, the higher the strength increase, and as ductility is the reciprocal of strength, it reduces. That is, the greater the strength resulting from work hardening, the lower will be the ductility. So as we work harden the metal, it gets stronger, but it gets less ductile, less malleability. Ductility being the ability to be deformed or shaped without failure. Now in the graph, you can see we are plotting strength on the left-hand side vertical axis and ductility on the right-hand axis. And in this picture, we see the annealed grains where their strength is low, the red line, and their ductility is high. As the degree of cold work increases, the deformation of the grains increases, so the strength increases and the ductility reduces. And as the cold work increases, maximum strength will be developed with the maximum deformation. So as we've severely cold worked the grains, as you can see in the slide, we've developed extremely high tensile strength, high strength. However, the corresponding ductility is becoming exhausted to zero. And if we carry on working, we will end up with brittle failures because there is no ductility left. So the limiting factor, there's a balancing act between strength and ductility of cold work metals. The limiting factor of the maximum strength we can develop is that ductility can be reduced to the point of brittle failure. So let's look at a little bit about annealing and recrystallization. So when a heavily cold work metal is heated to about 50% of its melting temperature, aluminium alloys typically melt in the range of 650, 660 degrees C, so around 300 degrees Celsius. If we take a heavily cold work metal and heat it up to that and hold it on that temperature for a period of time, new grains will start to form. So we've got a heavily cold work structure, as you can see in the picture. If we take it to about half of its melting temperature, new grains start to form. And the new grains grow from the old heavily deformed grains, consuming all those heavily plastically deformed grains. This grain growth process we term recrystallization. This temperature, approximately half the melting temperature of aluminium, we call the recrystallization temperature. And the process of growing new grains from the old cold work grains, we call annealing. Now, when we cold work a metal, we deform the grains, we put a lot of force, a lot of stress into a lot of energy, and cold working traps some of the energy to cold work within the deformed grains. When we anneal, we grow new grains. So annealing is a function of the degree of cold work. Remember, we have trapped the cold work, the energy within the grains. So the greater the amount of energy that we've got trapped, the greater the amount of cold working of those grains, the quicker and the easier the grains will anneal because we've trapped it. So hence growth of new grains, annealing is a function of the degree of cold work, the temperature, and time. The greater degree of cold work, the faster the annealing rate, The higher the temperature, the faster the annealing rate. So when we anneal a metal, we take it up to a temperature approximately half the melting temperature, hold it on time, and new grains start to grow from the old cold worked grains. With time, completely brand new grains regrow from the old grains, and we term this process annealing. And annealing is a time and temperature function.